The topic of the report is the battle distribution faction for cooperative spectrum sensing against the Byzantine attack in cognitive wireless sensor networks. I will start from the following four aspects. The first part is the background and the introduction. With the development of the wireless communication technology, various types of the sensors are eager for more spectrum resources. Nevertheless, lower spectrum efficiency of the current wireless communication technologies remains a significant bottleneck for further development. In order to explore more spectrum resources to support sensor and its related applications, cognitive wireless sensor networks, abbreviated CWSN, have emerged to identify available channels being underutilized by the primary users. The figure shows a CWSN including primary user and the sensor nodes. Two kinds of the members have different priority to spectrum access. By means of the spectrum, when the sensor node has detected that the target channel is underutilized by the primary and then use the spectrum in an opportunistic manner. If the sensor node has detected that the primary user is utilizing the target channel, then the sensor node must immediately free up the channel for the primary user without causing interference to primary networks. The spectrum sensing is a critical function of the CWSN, where the sensor node makes use of the local spectrum sensing techniques, such as the energy detection, match filters, and the stationary detection to gather information about the activity of the primary user. In this paper, energy detectors are exploited due to its lower complexity. Due to the shadowing, fading, and tire-wearing characteristics of the wireless, the single-node spectrum sensing will bring much uncertainty. Hence, the cooperative spectrum sensing is proposed to make more accurate global decision by fusing the result of the multiple sensing nodes. But cooperative spectrum sensing is vulnerable to Byzantine attack. The second part is the highlights of the article. There are two main parts. In the first part, in order to characterize the Byzantine behavior of the malicious sensor nodes in cooperative spectrum sensing, a flexible Byzantine attack model is proposed. The traditional attack model is always easy to detect because its behavior pattern is predictable. If effective monitoring and detection mechanism are designed, attackers may be quickly identified. The flexible attack model proposed by us can realize the various attack strategies and attack scales by arbitrarily adjusting parameters alpha and rho. By introducing randomness, dynamic attack makes the attack behavior more difficult to predict and detect, and can avoid some simple detection mechanism. The second part, in order to accurately evaluate the reputation value of each sensor, we developed a better distribution function algorithm to identify malicious sensor nodes. Firstly, a spectrum sensing frame structure is introduced. In the spectrum sensing frame structure, a frame duration includes a sensing slot, a reporting slot, and a data transmission slot. The better distribution function consists of the three parts: sequential process, battle reputation model, and the weight evaluation. Sequential process is that the all nodes report sensing results to the fusion center in descending order according to reputation values. According to the received sensing result, the fusion center makes the global decision on primary user status through a specific diffusion rules. When the number of the samples received is enough to make the global decision, there is no need to transmit other samples. At the end of each sensing frame, the fusion center assigns a reputation value to every node based on the battle reputation mode to identify malicious attackers and mitigate their subsequent impact on cooperative spectrum sensing. Next, the specific concepts of the battle reputation model are introduced. That acts represent the actual local sampling result transmitted by the samplers, and Y represent the local sampling result after being falsified by malicious samplers. R denotes the number of the occurrence of event X, and S represents the number of the occurrence of the event Y. By setting beta 0 is equal to R plus 1 and the beta 1 is equal to S plus 1. The probability density function can be shown in equal 11. The expectation of the event X shown in equation 20. Finally, the reputation value of the ion sensor node is evaluated by beta function in equation 13. Due to the negative impact of the Byzantine attack, the global decision may be unreliable. Therefore, a weight value is designed to participate in the final likelihood ratio calculation to make a reliable global decision. The fusion observes the false alarm and the misdetection. Then measures the local sampling result without being affected by a Byzantine attack. We label it as the GK and use it as a standard to measure the reliability of the local sampling result. The result deviation at the K sampling can be given by 14. Then the average value of the sampling result deviation is given by 15. Next, according to the deviation of the two sampling result, a positive or negative the evaluation value EIK is assigned to the ion sampler node when the average value of the sampling result deviation is greater than the result deviation. The local sampling result is reliable, and the sampling node is given in the positive evaluation and vice versa. Considering the storage capacity of the fusion center, we assume that the historical evaluation values of the sampler is L, which means the fusion center retained the valuation values that vary from L's instance of a sampling result. Therefore, the positive total evaluation PIK and the negative the total evaluation NIK of the I sampler and the K sampling are shown in equation 16 and 17. The total evaluation is then incorporated into the beta evaluation system. Specifically, for the ion sensor during the K sampling, the calculated evaluation values are considered. The reputation parameters, the RIK and the SIK, are expressed as 18 and 19. Finally, the reputation value or weight of the weight of the ion sensor after the K sampling can be expressed by 20. The third part is the performance analysis. The weight value obtained by the beta evaluation model is used to calculate the likelihood ratio in 18. And finally, the fusion center makes the global decision on a primary user state according 5. The whole model is built to realize the more efficient and secure cooperative spectrum sampling. So the performance of the system is exempt from error probability and the sample size under different attack models. The fourth part is the simulation result. The first set of the graphs shows that the influence of the attack scales on the error probability and the sample size under the always attack model of the different algorithm. It can be seen that the proposed beta distribution function has always maintain a very accurate primary user detection, and only a smaller number of the samples are needed to accurately detect the primary user. The second set of the graphs shows that influence of the attack probability on the error probability under different attack scales. It can be seen that the performance of the proposed beta distribution function is superior to other algorithms regardless of the attack scales. The third set of the graphs shows the influence of the attack probability on the average number of the samples under different attack scales. It can be seen that the average number of the samples of the proposed better distribution function is significantly smaller than other algorithms in both the large scale and the small scale attacks, and it changes stably. The simulation result shown compared with the other algorithm we proposed, better distribution function algorithm can obtain better performance under the flexible Byzantine attack model, and it is more effective in terms of the error probability and the average number of the samples, and can achieve more efficient and secure cooperative spectrum sampling.